there recently from UC Santa Barbara. His group has done a lot of really great work on understanding robustness and privacy in a variety of settings. And today he's going to be talking a bit more about some recent work on deep learning theory. So let's give him a welcome applause.
Thank you, Spencer, for the kind introduction, and thanks, organizer, for inviting me. It's great to be back to Simons. I always like it here. I was here for the reinforcement learning program a little bit and differential privacy. So every time I visit Simons, it's some of the best time that I had sharing with my colleagues and getting some of the collaboration done. So today I'm gonna talk about something new that we're just starting as a group. So the purpose of the talk is to share with the RED community who are actually expert on these topics what we've been up to, and get feedback and get the pointers on how we're gonna take this research program forward. Okay, in particular, I'm gonna talk about something really simple. I'm gonna be talking about curve fitting. And on the other hand, I'm also gonna connect it to some of the common hyperparameters that people tune in training deep learning models in practice, and hopefully gonna shed a light on some of the other topics that everybody else has covered at this workshop and during this semester's program. Okay. So I'll start with this quote. Like people have been saying this forever. Is deep learning just curve fitting? Right. So some people said it in a causality context by saying that, oh, you cannot be causal, it's not robust to distribution shift. But on the other hand, I just didn't like this word just. It appears as if curve fitting is a very simple problem. It's really not. It has nearly more than half a century of associated research. It's called non-parametric regression in statistics, denoising and filtering in signal processing and control. And it's really the backbone of a lot of the more challenging problem that deals with the information and denoising and processing the signal in the most optimal way possible. Okay, and there had been a lot of methods that have been proposed over the years, and we now understand like how to fit a smooth curve nearly optimally in almost every setting that's imaginable. On the other hand, it's never really about whether you can curve fit. Of course, like deep learning models can fit a curve, right? Can estimate a univariate function with a noisy observation. But it's more about how efficiently you can do that and how well you can do that, whether you can do that optimally in some sense. Okay, so here's a basic setting, right? Very simple. You observe noisy observations, yi's, at some fixed input grid, right? Xi. So this Xi can be sampled IID. It can also be the fixed design setting that Ryan talked about in the boot camp. Okay, you get this feature label pairs, but like you make relatively weak assumptions on where this ground truth function f is coming from. Usually some complexity, some smoothness class, you assume it's Lipschitz, you assume it satisfies some of the other properties. Okay, unlike a parametric function where you assume realizability. And the mean square error is typically how we measure the performance of a non-parametric regression estimator. Suppose you construct a function f hat, and this is your estimator, and you compare that against the supposedly ground truth that has been generated the data. So rather than the label, but it is just directly connected to the label by subtracting sigma square, and then you get a good estimator for the MSE. Okay. And it covers approximation theory, estimation, and generalization theory, as well as we know the optimality of a lot of the function classes in non-parametric regression family. Therefore, it has become a perfect testbed, at least to me, because this is a problem I'm familiar with, to understand the fundamental properties of deep learning if we try to apply deep learning models to this simple-ish problem. For example, what functions can like neural networks represent, how efficiently they're representing it, and what happens when the neural network is overparameterized and then we train the neural network in a specific way, and how does the hyperparameter choices in training regularization is affecting the generalization of such networks' performance on such simple examples. Okay. Specifically, like we wanted to ask a slightly different question, and because in most of the non-parametric regression setting, we know what the minimax risks are, right? We know we have near optimal estimators that achieve the minimax rate over there. So perhaps it's not sufficient to just say that, okay, there exists a particular neural network configuration that if you do so, if you carefully construct the network architecture, then you can recover the minimax rate. But on the other hand, we wanted to understand why these deep models actually work better. Why it work better? What is the advantage of the deep neural networks and this procedure of getting the data, trying to find the architecture, tune learning rate, to tune weight decay, to tune other hyperparameters. That seems to work really well in practice in a variety of different settings. What is the advantage of doing that? People say that these deep networks are universal function approximators, but so are other things, like kernels and splines are universal function approximators. They say that it has a modeling language that can use it to encode a lot of inductive biases that you have about what happens in reality. But so are graphical models and probabilistic programs, and arguably they are more interpretable than the deep architectures. And in addition, there had been a lot of recent work on overparameterization. For example, the NTK theory and the benign overfitting theory, and most of these theoretical results focus on the interpolation regime, right? And sometimes it can be successful in solving non-parametric regression problems optimally, but as we'll see in this talk, right? So a lot of this existing theory doesn't seem to explain, interesting behaviors even in the 1D function in some like relatively simple regimes. Okay, so here's what we propose, right? So here's the the underlying philosophical idea behind these lines of research that we've been driving, called the adaptivity hypothesis. So neural network, they're just not stronger than any classical method, like for every instance of problem that we're solving, but instead, perhaps the advantage is in the adaptivity. So maybe by tuning the hyperparameters in the deep learning pipeline, we're not really, that saves the effort on the statistician or the modeler side to not having to carefully specify the problem, not having to know the right level, not having to know which function class this ground truth is coming from, and as long as you tune these standard hyperparameters, then you can achieve performances that matches or even surpass some of the best classical methods for each problem individually. Right, so this is a problem of what we call adaptivity, and it's the same notion of adaptivity that in terms of hyperparameter free that statisticians talks about a lot. All right, so here's the outline of the talk. I'm gonna just go over two of the recent work that we had. My group have done about the effect of weight decay or bounded norm in deep learning models, and the effect of large learning rate, right? When we train the networks with gradient descent. Okay, so I'm gonna have to skip the second part because this talk was prepared for a longer format of the presentation. But feel free to stop me anytime during the talk and ask questions, especially if it's preventing you from understanding the materials. I realize that sometimes there is a language barrier, like when I speak to people who are not from the same community. All right, so I'm going to zoom in a little bit further into a family of non-parametric regression problem called locally adaptive non-parametric regression. Right? By locally adaptive, I mean these functions are smoother in some regions of the space and more wiggly in some other regions of the space. I'm giving you this Doppler-like function on the left, right, which is more wiggly here, but smoother on the right-hand side. Right? This is a two-dimensional, like 2D image example. You can see that in the background and on the jacket over here is very smooth and very homogeneous, but at the boundary of the different objects, then there are sudden changes and not so smooth like regions that you also have to cover. Okay, so these are the locally adaptive non-parametric regression, and it is known that for methods like wavelets, adaptive kernels, and adaptive splines, and others, they are able to perform reasonably well on such problems by carefully allocating your statistical power to the appropriate amount of statistical power to the part of the space that you actually need for smoothing that region. So here's an example. So these are data collected from the gravitational wave data that captures the merger of the two black holes. And well, the green is a noisy observation, and the black is what you end up getting fitted into this Doppler-like signal through one of the methods that we worked with some time ago called train filtering. You can see that it captures what the intuition is saying about the two black holes rotating against each other and getting faster and faster. You can try to apply other smoothing methods on it. For example, smoothing spline, right? And now since we have general relativity, we can also plot the ground truth. And by comparing these two methods, you can see that train filtering is a locally adaptive method, while the smoothing spline is not. When you change the hyperparameter of the smoothing spline, right, this regularization term, so either you are able to fit perfectly on the left-hand side, but then you underfit the part that's more wiggly, or like if you make the regularization term smaller, then you'll have like much noisier like predictions on the left-hand side if you want to reach the same level of statistical efficiency on the more wiggly side. Okay, so there simply isn't a good hyperparameter choice for smoothing spline to match the performance of train filtering. So a natural question to ask, right, is the deep neural network in the smoothing spline family, or is it in the train filtering family, which are able to perform more adaptively? Okay, so specifically, this means that if we consider the input function being from what we call the total variation class or the best of classes, whether deep neural networks are still able to achieve the optimal rate. Okay, we're not the first to ask this question. There were prior work that studied this, Suzuki, Liu et al. So they studied this from more or less approximation theoretic point of view. They show that if you construct a carefully designed sparse neural network, and then you are able to and optimize only over those sparsely chosen weights, and then you are able to get the minimax rate. But the level of sparsity depends on the function class and the radius that you end up used in defining that function class. And Paki and Nowak, this is something I'm going to talk about just in a little bit. But the punchline of the first part of our results is that we designed a parallel like deep ReLU neural network, and as the depth gets bigger, then it achieves nearly optimal locally adaptive rates for almost the entire family of best of class, right? No matter what the parameters are, no matter what the specification of the smoothness functions are, and the only thing you need to do is to tune the weight decay parameter appropriately according to a holdout set. Okay. So that's kind of punchline for the first part. So, but before I start telling you about parallel neural network, let's talk about much simpler model, the two-layer ReLU neural network to build a bit of intuition. And I'm gonna actually compare it side by side with the L1 train filtering, which is the method that was used in the gravitational wave example. So on the left, I'm plotting the actual fit of the L1 train filtering on the input data. So these like little red dots. So those are the input noisy observations, and I'm fitting this curve to try to capture its behavior. You can see that as I increase the regularization parameters in L1 train filtering, right, the regularization term is like penalizing the integral of the second derivative, integral of the absolute value of the second derivative of the underlying function you are optimizing. And you can see that I say increase the lambda parameter, and you go from interpolating the data using piecewise linear functions into something that becomes flatter and eventually collapse to just a simple linear fit when the lambda gets too large. Interestingly, when we use gradient descent to optimize a two-layer overparameterized neural network with weight decay, and as we decrease the weight decay parameter from something that's relatively large all the way to 0, we actually recover a very similar pattern that matches the L1 train filtering very closely. Okay, there are some differences, like since we're not actually solving the exact minimizer for the two-layer ReLU, but yeah, it's reassuring that now they actually look very much like each other, which makes me wonder whether there are some deeper connections between these two methods. Yes. Oh, when I say two-layer ReLU neural network, so these are just the standard two-layer ReLU neural networks that I use to fit 1D input. Yes, one hidden layer. Yeah, 1D input, one hidden layer, like very wide. Okay. I randomly initialize the weights. Okay. There's another view of the same problem called what we call the regularization path. So this takes the corresponding coefficient of the individual basis functions and see like individual basis function. In this case, right, these are a bunch of little ReLUs, and for the L1 train filtering, they are the so-called truncated linear basis. And then as lambda changes, you can plot the evolution of this as a function of the regularization parameter. As you can see over on this plot, they also seem to match each other quite nicely, especially on the more right-hand side, but then they become a bit different in the more interpolating side, right? When everything is non-zero and L1 train filtering seems to be able to fit the data better than that of the ReLU neural network. But besides that, these are generally the same trend, right? So by tuning the weight decay, it seems that we are tuning the regularization parameters of the L1 train filtering. Okay. So to explain what is really going on, so I need to set up a bit since like who knows what a spline is already? Spline. Okay, most of you guys. Okay, so splines are just piecewise polynomials that are also happening to be continuous and satisfying some high order continuity at the knots. And knots are where the two polynomials are joined together. Okay, so these are like linear splines, quadratic spline, and cubic splines. These are just piecewise linear, piecewise quadratic, and piecewise cubic functions, and these locations are their knots. It's a very flexible family for representing curves that people use. And the key differences on all spline methods is how you choose this location of these knots. Smoothing splines, so basically choose all of the input data points as knots, and then penalize the square L2 penalty on the coefficients, right? To make all the coefficients small, so you end up getting something that's very smooth. The other method called locally adaptive regression spline uses use L1 penalty on the coefficients to try to find a sparse number of active basis functions. So it prefers like a spline with a smaller number of pieces. Okay, so these are the splines, and these are a particular set of basis functions that you can use to describe any spline by writing them as a linear combination of these functions, right? So you got linear spline basis and cubic spline basis, and in particular, like this should remind you of ReLUs. If you are using a two-layer, like one hidden layer neural network, and it's effectively like at the end of the day, like having a linear combination of a bunch of such linear spline bases. Yeah, that's how like a ReLU neural network always represent piecewise linear functions, aka splines. So one natural observation is that the two-layer neural network is not just approximating splines; they are splines. They are what the statisticians call the free knot splines. Whereas you not only optimize over the coefficients of the basis function, but also try to allocate the location of the knot to the appropriate places. And underparameterized two-layer neural networks use a small number of knots, but an overparameterized neural network uses a huge number of knots, sometimes even more than the number of data points. But then you're still optimizing over them, like using the standard techniques. So I'm now stating the neural network in a slightly more general fashion with this additional hyperparameter of m. So m is an integer. When m is equal to 1, then it gives you the ReLU. When m is equal to 2, it gives you square ReLU and the cubic ReLU. So this recovers high order splines as well. So not just the linear spline. And this is C and C tilde, so they represent the polynomial functions up to mth order. Yes.
So I guess free knot splines have occurred before, but how do people optimize them? Because it's non-convex.
It's usually heuristic. Right. Yeah. There's some tricks and sometimes Bayesian tricks to get you to allocate them, and before you fit again. There's sometimes a back and forth alternating procedure for selecting these knots.
So they never use like gradient.
Not that I'm aware of, but I'm also not an expert on this literature, so it could be. Yeah. I guess yes.
What Once you go to 2 dimensions, these are not exactly the same anymore.
They are not exactly the same anymore, but they become like rich splines, right? A combination of rich splines. Yeah. Okay, so the only difference is that the classical max method fix the location of the knots and regularize, whereas the neural network and free knot splines, they leave the location of the knots freely moving. Okay, so in the next slide, I'm gonna show you that way decay is actually equal to the total variation regularization. So take the neural network representation here, and then use the homogeneous property of this ReLU, right? This is sigma is ReLU, sigma taken to the power of m is still homogeneous when you extract a constant, non-negative constant out of here, right? You can multiply that constant to the power of m in front. You can always take the absolute value of this first layer weight wj and extract it outside the nonlinearity by raising it to the power of m. Okay, so you can do that and then combine that with this into this reparameterization. So this is Cj is now the coefficient of some mth order truncated power basis where the location of the knot is Tj, right? And what the Tj is in the case when Wj is positive, then Tj is Bj over Wj. Right, so that's the location of the knots, and you can massage the signs of this Wj by adding like everything that remains into this C, right? So you go from C to C2 that, but merge everything into the polynomial. So I won't bore you with the details, but then if you're minimizing some kind of a loss, right, over the neural network weights. So right now I'm ignoring the bias parameters, and the regularization term doesn't include the bias parameters. So only the weights parameters. So this is typically how people do it, anyways. And then the only tricks that we need is the AMG-M inequality, right? So these are the weight decay square L2 regularization raised to the power of m, right? But when m is equal to 1, this is a standard weight decay. But you can apply the AMG-M inequality. You can combine them and make them the multiplicative form, and you immediately realize that the term on the right-hand side is actually this coefficient Cj, and whatever loss function that you have, it only depends on the functions that this neural network represents. And therefore, when you are minimizing this objective function, it's without loss of generality that you always want this inequality to take the equal sign. Does everybody follow that? Right, you're minimizing this, but it is only the right-hand side, this expression, that actually goes into the loss calculation. So therefore, right, for any for any vi and wj to the power of m that's not balanced, the optimization algorithm will always take you to a corresponding rebalancing such that the objective function is lower. Okay, so we didn't wait. Yeah, so we didn't invent this. So this has ages of history that went back to Bingham and Natti's work. It actually went back much older to this matrix factorization literature where they are penalizing the Frobenius norm of the two factors and ended up constructing the nuclear norm. So this is just the sparse L1 version of that. But then later this is used in a lot of different contexts in understanding neural networks. So nothing is new here. But what is nice is that once you convert this into the sum of the absolute value of the coefficients, you realize that the absolute value of the coefficients of that truncated power basis actually recovers the total variation. The total variation of the function itself, and the interesting result from Paki and Nowak is a representer theorem type result that shows that as long as the neural network is sufficiently overparameterized, in the sense that the number of knots is larger than the number of data points minus the order of m, then solving this neural network to the global optimal regularized ERM solution is equivalent to solving this variational problem with over the space of all functions, which turns out to be the estimator that Manman and Vandergeer constructed called locally adaptive regression spline. Okay, and this method is shown to enjoy the near optimal rate in estimating the total variation function. Okay, therefore, if you are able to solve neural networks computation problem, you have a neural network estimator that matches what is known to be minimax optimal. And since if and the tuning the weight decay parameter is equivalent to tuning the regularization parameters in the locally adaptive regression spline. Okay. Yeah, as a quick checkpoint. So this is just a simple example to show that to answer the initial questions that I proposed. Can neural networks be locally adaptive, and whether it is in the smoothing spline camp or it is in the trend filtering camp? It turns out that it is in the trend filtering camp. It can be locally adaptive. It's a lot better than any kernel-rich regression. Okay, the limitation is also obvious, right? What happens if the input function satisfies the higher order degree of smoothness? What if it's not a linear spline? Well, what if the input function's regularity condition depends on the third derivative or fourth derivative? Can we take advantage of that and get better estimators? And also, like, this is just a two-layer neural network, right? So in practice, people discover that increasing the depth of the neural network is actually making things a lot better and stronger, and maybe not easier to learn, but definitely a lot more learnable with a small number of samples. Yes. Yes.
When you say locally adaptive, that's still a necessary condition for getting a minimax rate, right? Or does locally adaptive mean that you're adapting to sort of more benign instances?
Oh. I'm meaning local adaptivity in a very technical sense. It means that it achieves the minimax rate on the functions with heterogeneous smoothness.
I see. This is locally spatially adaptive.
Okay.
Not locally adaptive in the sense that Max is thinking.
I see.
Basically, local spatial adaptivity is needed to be minimax because the heterogeneity requires.
Yes.
Okay, that clarifies.
Yes. Yeah. I should clarify. It's locally spatially adaptive. All right. Yeah. So the question is, can we generalize the result? So here's what we did. We defined this L-layer parallel neural network, which effectively take every neuron and replace that neuron in the two-layer neural network with a deeper architecture. So now we have M, parallel but tall and skinny kind of neural network that goes from the univariate input all the way to the univariate output. Okay, so that's it's a special case of the standard L-layer ReLU neural network, but there's this block diagonal predefined, the hard-coded sparse structure that's imposed on there, so that you recover this parallel structure. Okay, so we also didn't invent this, and in ResNet and in other parallel structure had been proposed before, and people studied this and tried this out on vision and language problems, and it seems to be working, pretty effectively on a lot of tasks. Okay, and the key idea is actually the same. So now that everything is ReLU, not the quadratic ReLU and cubic ReLU. So ReLU activation function is one homogeneous. So what we can do is to take the weights of every single layer and take its two norm and push them all the way towards the end, and then reparameterize the neural network into a constrained form in which you recover this coefficient. So these A1 to AM were the C1 to CM from before, but these W are now changed into W bar. And these W bar are the normalized version of this original W. Right, you can check that from the one homogeneous properties. There's a one-to-one mapping between these two slightly different architecture. But this is nice. This is saying that I'm rewriting this in a very interpretable form, in a form of a linear combination of the set of learned basis function. Each one of these basis functions is represented as a neural network. Okay, to say it differently, we've parameterized this L-layer parallel neural network into this familiar linear regression form with labels over there and a long coefficient vector, but then with a dictionary that we represent every we represent every column of this dictionary to be evaluation of that neural network on the input data points. Okay, and wait. with okay. And the nice thing is that the AMGM inequality argument still works, but now we have L copies of them instead of just 2, right? But if we use AMGM inequality, it doesn't recover the L1 norm of the coefficient vector. Now it recovers the LP norm of the coefficient vector. The LP norm when P is equal to 2 over L, which means that the deeper the neural network that we used, the sparser that we impose, the sparser constraint that we impose on this coefficient vector. And that turns out to be very handy when at the time of proving generalization, right, for such neural architecture. Okay, I'm not gonna go into a whole lot of details about defining these function classes, connection to total variation. We're using the same mean square error metric, and we're considering the sub-Gaussian noise, independent sub-Gaussian noise case with either fixed design or random design. It doesn't make a difference. But here's the result that we can state about a weight decay or norm constraint estimator for this parallel deep neural network with L layers and M parallel component. So what we can prove is the following: for Bessel class and bounded variation class, these are very complicated. But if you just take this L to infinity, you can see that they exactly recovers the minimax rate for both the Bessel space and boundary variation space. And the nice thing is that we don't really know like which function class this underlying ground truth data is coming from, right? And the only hyperparameter that we need to tune is set this M to be large. So we basically set the number of parallel blocks to be larger than the number of data points, and then we shrink. We shrink it by tuning the weight decay parameter. And according to the previous insight, then the weight decay corresponds to the 2 over L norm on the coefficient, which really drives the sparsity down. So at the end of the day, you end up getting this kind of rate, and when you take L to be on the order of logarithmic in n in the number of data points, and then you can be simultaneously optimal for all choices of alpha and all choices of the radius of these function classes, and end up getting the best of all the world. Yes. Yes.
So what precisely is that unknown object that you're not automatically adapting to?
We need to tune the weight decay parameter to balance balance these two bonds, and we also don't know what alpha is, right? We know D because that's the input dimension. We don't know the alpha. Alpha is the smoothness parameter of the input unknown function. The tuning of weight decay doesn't need to depend on alpha because you can just use a fixed exponential grid.
What does it depend on? What is the precise object that the weight decay parameter has to depend on?
We propose to use a cross validation. Yeah, you use holdout to tune the weight decay, right? Which is what practitioners do, right? Yeah.
Oh, right.
Yeah, we do hyperparameter tuning, and these results are stated for the best hyperparameter.
I see. So part of the adaptivity does require this hyperparameter tuning, but part of it
but it does only require the one standard hyperparameter tuning rather than trying out the different minimax error and radius. Yeah. Okay, so a few interesting insights we can read off from the theorem. First of all, there's a formal separation from the kernels. So kernels cannot achieve the minimax rate. They can only achieve the minimax linear rate, right? If you take alpha to be 1, right, and D to be 1, this is n to the minus 1 over 2, and the minimax rate is minus 2 over 3, right? So sometimes it's a substantial differences. And second, as the depth gets bigger, the error actually gets smaller. But this one is not very strong because we are only comparing the upper bounds that we are able to obtain, right? So some of the metric entropy calculation, if we can improve it further, so it's possible that we can eliminate the dependence on the depth altogether, and which would also recover the 2-layer case. And overparameterization, in terms of the capital M, the number of the total number of parameters of the network doesn't really cause overfitting. But this is nothing interesting because it's due to our explicit regularization through weight decay. But the method the geometry that it is preventing overfitting in the overparameterized regime is actually interesting. It's due to the implicit sparsity in the learned basis function space. Yeah, that turns out to be sufficient to give you like a nearly optimal rate. And if we compare to classical non-parametric regression method, you can see that they all have the form of a linear combination of certain basis function. But the difference is that in the classical method, these GI functions, they are hard-coded, predefined. But in the parallel neural network, each one of them are learnable components. And you basically learn the dictionary and then learn the sparse linear combination of that basis function in the dictionary at the same time. Yeah, that turns out to be the trick that gives you the adaptivity. Okay, so let's look at a few experimental illustrations of the result. So on the left, I'm plotting the noisy data together with the ground truth function and the fit from smoothing spline train filtering and parallel neural network. You can see that the parallel neural network and the train filtering, they are able to fit the more wiggly parts a lot better than that of the smoothing spline. And this shows up in the mean square error as you change the hyperparameter of each individual method. I'm plotting the degree of freedom on the horizontal axis. So this is the metric for complexity that Ryan talked about in the bootcamp. And on the right, this is something that's actually interesting. So these parallel neural networks, they are very overparameterized. So we use thousands of like parallel blocks, but these are the only ones that ended up surviving. These are the only ones that doesn't have their weights to be exactly 0. I'm counting like 6 of them, and it's funny that some of these parallel block they recover they are covering the higher frequency region, and others are covering the lower frequency region. They're not exactly like wavelet transform, but it's doing something similar, right? It's allocating the different statistical power and the different basis function to be in charge of the different region of the space. Yeah, with appropriate periodicity. We made the problem slightly harder by making this function like piecewise. In the first piece is piecewise linear. In the second piece is piecewise cubic, right? So no except wavelets, right? No existing classical non-parametric regression methods natively handles this kind of scenario, right? So either you need to commit to fitting a cubic spline or a linear spline, right? You can't do that before knowing where the transition point is. On the other hand, like it's natural for this kind of basis learning type of algorithm, like parallel neural network, to capture both these two phenomena at the same time. And you can see that like it ended up getting the best mean square error at the appropriate degree or level of degree of freedom, and the kind of learned basis function is also interestingly capturing the underlying structure of the ground truth. Okay. Forward. As a quick checkpoint. So I've told you about the parallel neural network and how weight decay helps you to get this incredible adaptivity, right? For these simple-ish problems in low dimension. It adapts to the smoothness of the input function. Unfortunately, it incurs the dimension dependence on the exponent, and this is necessary because we are trying to fit function in the very large family of problems. Okay, so I'm gonna skip the second part. This was planned, but the idea is to deal with this D parameter by calling this D the ambient dimension, making some assumptions on the data distribution, saying that they actually fall under a smooth manifold, right? That can be unwrapped into more or less into like little linear pieces, and then you can define an underlying Bessel space function on each piece and then connect them together. It turns out that under that model, you can replace this D with the intrinsic dimension of the underlying manifold without knowing what D is. Okay, so I'm gonna skip this part altogether and get to the last part of the talk, which is how the role of optimization in all of this. So I've never talked about anything about optimization and computation up to this point. Okay, everything is about the regularized, nonlinear least square, right? We assume we can get the regularized empirical risk minimizer, which is intractable in general, like due to the non-convex nature of the problem. On the other hand, in practice, people optimize these networks using gradient descent. It seems to be doing fine. Let's see if we can try understanding the behavior of such a gradient descent, in fitting such one-dimensional function, even if we do not impose any weight decay. Okay, so in this case, let's forget about regularization, but train the gradient descent on a two-layer ReLU network. And restrict ourselves to this TV1 function, and then try to understand the effect of large learning rate. So let's start with an example, right? So it's late afternoon, everybody's tired. So let's consider this example to get everybody to wake up. So on the left-hand side, we have 30 data point, noisy, and the blue line is the underlying ground truth. Okay. Ground truth plus noise, ID noise, you get this noisy observations. And we're fitting a two-layer overparameterized neural network with 1,000 neurons to this simple example with merely 30 data points. No regularization at all. And we're using square loss. So which one of these A, B, 3 choices are true? Who thinks A is true? Raise your hand. This is about just... Okay, almost every half of them, I guess, other people who think A is not true, A is false. Nobody. Okay, so that's 100%. Yeah, absolutely. Yeah, this is only about approximation, right? So you can interpolate the data very easily with 1,000 neurons with 30 data points. You can just connect them in linear pieces, and that's something that this neural network can represent. Second option, gradient descent finds a global optimal interpolating solution. Who thinks this is true? Raise your hand. All right, so many of you. Yeah, with respect to training. Yeah, with respect to training. Okay, many of you. How about the third one? This solution satisfies benign overfitting. So for those who don't know what benign overfitting is, it says that even though you interpolate the test error, if you redraw these samples from some IID distribution, and then the test error is actually okay. The test error is actually going to 0 as n gets bigger. Who thinks it satisfies benign overfitting? Who thinks it satisfies like temperament overfitting? Who thinks it satisfies catastrophic overfitting, which says the error goes to? Okay, a few. Yes.
Stopping gradient descent?
You keep optimizing it until you converge.
Why?
Or until whatever, indefinitely. I'm talking about steady state of gradient descent. I'm not really stopping.
Why?
Why? Yeah, I could, but this is my way of optimizing it. I want to get the smallest training error possible. Okay, so A is clearly true, but B actually depends. Yeah, B actually depends, and it's surprisingly difficult to get this gradient descent in any practical hyperparameter regime to actually overfit to the data, to actually get to zero loss. C is clearly false. So there's a paper that talks about this and say at least in one dimension, benign overfitting doesn't happen for two-layer ReLU networks. So you'll see a bit more of that later. So here's let's try actually fitting this model with a gradient descent. So now I'm gonna choose a gradient descent hyperparameter. So the only hyperparameter here is the learning rate. Let's choose learning rate to be 0.5. Right, this is a fitted function that I get as a steady state. I run it forever, and very quickly get to this point and never move anywhere at all. Right, so I get a flat function. So let's reduce the learning rate. I reduce the learning rate to 0.4, and this is a function that I got. It introduces 2 knots. Okay, and nice, like this is MSE, right? So it doesn't go up, but the training loss doesn't go down. It's very far away from 0. Yes. Yeah. 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 Actually, it isn't affected by how overparameterized it is.
I think it's very sensitive on how you initialize the biases.
Oh, yeah, right. So I tried everything. I tried NTK initialization. I tried the mean field initialization. I tried other things. Right? The one that I ended up using that helps this method to optimize a bit to initialize it in some sense uniformly, such as the location of the knots is uniform between -0.5 to 0.5. Right, so that's the initialization I use. I helped it a little bit, but you know it still doesn't seem to overfit. Okay, so let's decrease it further. The more I decrease the learning rate, like the more change points, the more linear pieces that seems to recover in the fitted function. And then I start to see the test error start to increase as I keep optimizing, and eventually, as learning rate becomes very small, then I ended up getting this blatant overfitting. Right, I think if I keep optimizing this, and if this eta gets even smaller, and I optimize even longer, like notice that this is already 10,000 iterations. As I decrease the learning rate, I need to increase the number of iterations so that it covers the same ground, right? And then I'll eventually end up getting sigma square over here and interpolate every single data point. But the point is that it depends. The answer to B is that it depends. It needs a very small learning rate, and we're able to characterize this theoretically. So we have a result in the paper that shows that you need the learning rate to be smaller than 1/n squared, where n is the number of data points, multiplied with sigma, and sigma is a noise level for you to actually interpolate the training data. Another thing is that it's clear that the functions that you end up getting are still piecewise linear. Right, so if you get a piecewise linear function of the noise, you can never really get anywhere near the ground truth, right, in terms of the MSE. So those examples of benign overfitting happens when you have very spiky observations over here, right? So you spike up here, but then very quickly you damp back to where initially is, right? So it's possible, like for data points that are near you, your average performance is still still okay, but that doesn't actually happen in this example, Jingfeng. Right. Yeah, that's curious. I don't know. It's possible that it added some non-zero components. It was a 0, but then if you keep optimizing, that ended up. Yeah, it's curious. We're using a fixed learning rate to optimize, so we're not sure like why there's a little bump. Yeah, there could be it's entering a different regime, and after that it enters an NTK type regime, right? But before that, it might be the representation learning regime. Yeah, the learning rate is still too large, right? As I said, like with the data point being 30, like it should be 1/30 square. Right, multiply with the sigma. So that's the learning rate that we showed that it needs to be smaller than that in order for the gradient descent to interpolate. Okay. Yes.
Is it connected to the Edge-of-Stability behavior, or is it like when network gets in Edge to achieve interpolation?
Yeah, so that's the thing. So most of the NTK regime like assumes the input data is on the unit sphere of some high dimensional space, but in over here the input data is 1D, right? If you normalize it to unit norm, then you trivialize these things because all your data points are going to be either at -0.5 or 0.5, -1 or 1. Right. So I actually don't know like what's going on here and why is it this difficult to get the gradient descent to converge to interpolating solution. But the point is that it's a boom. It's not something that's malfunctioning. So I hope this picture changes. So your view about optimization and the generalization a little bit. And sometimes like you don't want to converge to interpolating solution because interpolating solutions are bad. Right? There are very interesting cases about the benign overfitting, but in my experience, at least for this 1D problem, it's kind of a property that if you satisfy interpolation, then you cannot generalize. And if you want to get any solutions that are consistent with the MSE that's going to 0, then you need to avoid at all costs to convert your algorithm to actually converge to the global optimal solution. Instead, you want to convert to some local optimal solutions that are like in some sense better, that has an error that's around the sigma square, because that's what a ground truth would have produced. sigma square, right? It's a set point that you should be aiming for. So maybe we can regularize towards that. So anything that's above or smaller than sigma square, that we should ask it to come back to that kind of loss function. So so how do we connect this to learning rate? So one way is through the optimization theory. So everybody knows the convergence of gradient descent, right? So if you have optimizing a function that's beta smooth, then when you choose the learning rate to be strictly smaller than 2 over beta, then you have a convergence sequence to a stationary point. Do I have okay, sure. And in deep neural networks, the smoothness is location dependent. So in some local minima, it is flatter, and beta is small. In some other local minima, beta is very large, right? So the effect of like large learning rate in gradient descent is to somehow select the set of local minima you can actually converge to, you can actually commit to. Okay, so one can see this from the edge-of-stability setting as well. So this is what the edge-of-stability papers has produced, that is a cleanness among all their experiments, and what they use is a square loss type regression. And we know that for the square loss type regression, our results is the most precise, and it turns out that if you keep optimizing, then there's this what they call a progressive sharpening regime, and then once they reach 2 over eta, they stabilize this around solutions that with the sharpness being exactly the same as 2 over eta. It doesn't go higher, it doesn't go lower. So here's the mental picture about this part of my talk. You have all these functions that an overparameterized neural network can represent. It's huge. It has a large VC dimension. But the set of solutions that gradient descent can actually find with a fixed learning rate is significantly smaller. And this covers both the minima stability regime and edge-of-stability regime that has been studied in the literature. So I have 5 minutes. I'm gonna just go very, very quickly to interesting part of the stuff. So I guess the first thing that we wanted to understand is what sharpness has. How sharpness and this learning rate type constraint on sharpness is affecting on the shape of the function. Okay, so it turns out that it becomes something that we have already seen in the first part of the talk. So it turns out that besides this weighting function, which is independent to the shape of the regression function at all, it only depends on the input distribution, and this is some sort of weighted TV1 class. This is a weighted integral of the second absolute value of the second derivative of the function that neural network represents. So this is a superset of the set of functions that are sufficiently flat. Okay, and this the parameter c is equal to 1 over eta plus a small constant term. What is g? G is a weighting function that depends only on the input data distribution. It's more Laplace-like, that's bigger in the middle and smaller on the tail of the data support. Okay, so what we can prove is that this weighted TV1 radius is bounded by the sharpness, even without assuming interpolation, right? So previously it was known that if you assume interpolation, you can get results that looks like this. With this being, just minus 1 over 2. But our extension to this work is to say that now in any situations, interpolation or non-interpolation case, you can come up with bound on this function class characterization of the set of functions that neural network can converge to by expressing them as the sharpness, right, which can be further bounded by 2 over the learning rate, plus some constant terms. In the fully agnostic case, right, this constant term depends on just a loss function that you're minimizing, right? If you get small loss functions, then the function class becomes smoother. And in the regression setting, when you have IID noise, the signal plus noise setting, this part only depends on the MSE, right? So the loss can be sigma square, can be small, but as long as the mean square error of your current estimator is, then this term can go to 0. And this middle term actually comes out of some sort of a Gaussian complexity term that we further bounded with this number of neurons. But in the overparameterized case, we can easily bound it with 1. But folks as creative and clever as you guys might come up with better bounds on this, so that in this regime, like this term in the middle actually goes to 0 as well. So empirically, we do see that the term in the middle like becomes negligible compared to everything else. Okay, so I'm gonna skip the proof idea, but yeah, this should be the standard decomposition of the Hessian. So people studying the NTK theory should have seen. I'm also gonna skip over this. Yeah, we showed that in the strict interior of the data support, right? This the implicit bias introduced by large learning rates is sufficient for getting the estimation error to behave in a way that's minimax optimal. Therefore, also separating deep learning training without weight decay, and when you compare that to kernel methods such as NTK, like this is strictly better. Okay, 2 more slides. I'm gonna wrap up. The first thing in these 2 slides that I'm gonna show is a mental picture of the loss landscape. So in overparameterized neural network, there are a lot of such interpolating solutions that with nearly 0 error. Like the goal of an optimization researcher is often to find as small a loss as possible. But what we have seen in this talk and in this sequence of work, that's a small loss, like we cannot bet on benign overfitting to save us from the perils of these interpolating solution. In many cases, any interpolating solutions are actually bad, right? And in this case, we can characterize the shape of them. They are all very sharp. Their sharpness, the largest eigenvalue over there, they are scaling with n square. Instead, we should find like solutions that are more moderate, that respect the noise level. The other aspect is representation learning, right? On the left this is the kind of basis function that we initialize the neural networks with. On the right, so these are the basis functions that we ended up learning with a large learning rate neural network training. You can see that we ended up getting a lot of sparsity, right, in the basis function. But the interesting thing is that once I look into the details of how this works, they are not actually completely flat. Over here, like you can see that maybe only two basis functions are active and everything else are completely killed off. But it's not actually the case, right? In this implicit bias induced sparsity. What happened is that all of these other basis functions are simply pushed all the way to outside the data support, so they appear to be completely 0. So this opens up to chances of adversarial attack, right? And other possible issues that leverages those that doesn't has an impact on the training or test error, right? Because those sparsity are not real sparsity. I saw one of the knots is actually a -800. I have no idea why that happened. Yeah. So with that, I'll conclude. So some implication of a modern generalization theory. So this is topic of the workshop. In the classical generalization theory, we rely on the uniform convergence theory. We don't deal with optimization at all. It's completely decoupled. In the modern generalization theory, like there are more tools that are available. There are more interesting phenomena that we wanted to understand, like the benign overfitting. And it has everything to do with optimization. The bar is typically you want to analyze the optimization dynamics so that you end up understanding the point that you actually converge to, or the distribution that you converge it becomes stationary on. And the dynamic theory, however, is very difficult for complex settings, and it's very difficult to scale it up to the type of architecture that people study. So the high level moral of the story in my talk is so maybe we should consider something in between, right? So I would group algorithmic stability to also in this regime of in between that kind of deal with the optimization, but doesn't deal with optimization in the same way of the NTK theory of the like gradient dynamics theory. But instead, we can talk about the implicit selection property of these optimization algorithms and still understand the structure of them and then rely on the classical generalization theories techniques to analyze their uniform convergence, therefore like generalization. And what we've seen from the talk is that sometimes you can actually get optimal bounds. Okay, I'll wrap up, sorry.
Question?
Yes.
Yeah, so you showed this result that you get very few linear pieces for fixed learning rate, but if you make your learning rate decaying, that's not going to fix the problem.
Yeah, that's a good question. I think that the process of killing off those basis functions is very difficult to recover, right? So once some of the basis functions are killed off, right, you don't get any feedback anymore from the training data. So decreasing the learning rate in the later phase, I think, will not actually bring them back.
So you have to start with a small learning.
Yeah. So that's easy experiments to run. We didn't run it.
I also had a question about, you said, I've tried to run experiments on neural networks in 1 or 2 dimensions with noise, and I've never been able to succeed in getting it to interpolate. I mean, mainly in classification settings, so I haven't tried regression, but I'm curious. You said you seem to allude to having some success in some instances. What were the tricks that allowed for?
Yeah, when the noise is low and when the learning rate is small and you run it forever, then you sometimes can interpolate. So it's much easier to interpolate when you fix the first layer and then just optimize the second layer, and then you almost always interpolate. You can even just solve a least square problem, right? But then that's one of those global optimal solutions, right? That could correspond to some asymptotic limit of training the neural networks with gradient flow, right? But yeah, I had similar experience, right? When the data is noisy, it's almost impossible to overfit, right? To interpolate. Yeah. Then?
Yeah. So as a complete outsider, so here's one way that can maybe possibly interpretation of the results you show, right? So what I think the moral of the story we want to say is that even if you achieve interpolating solution, it's not good. It's not a good. It's a poor solution for that problem. That's.
Yeah. If benign overfitting applies, then it could be a good solution. But in this case, I'm constructing an example. It's not.
Yeah, but given all the different learning curves and results that you show, it seems like nothing works there. Is that fair to say? Is it possible that in an instance where it just nothing works, then anything will fail? So
no. Some of them actually give you pretty reasonable fit, right? In this example, right? This is about the best you can get. Yeah, with a very noisy data, right? So how do you get better than this, right, for fitting the blue line?
I think that's the point. It's the data is too noisy that. Yeah. Also.
Yeah, but that's the point of signal processing and denoising, and you deal with noise that are significantly larger than the signal you want to behave optimally in that regime. Right, but increasing the signal to noise ratio as much as you can.
Yeah, but even this one, it could be just you run a lot of things and just happen to be the case that something seems to.
I see. You're worried about hyperparameter tuning of one or two dimension. Okay.
This instance, this learning problem, given your neural net, may be just hard anyway. So no guarantee should be achievable whatsoever. Maybe that's too pessimistic, but just looking from outside, this could be one explanation.
All right. Yeah, we can discuss a bit more offline. Yeah.
Maybe we can conclude here.
Thank you.
So we'll start in 15 minutes, 3:35.